All right, so today I'm going to be explaining another important paper with the title Slice Score Matching, a Scalable Approach to Density and Score Estimation. This beautiful paper in 2019 by Stanford University. Professor Stefano Erman has done a great research in machine learning, especially generative models, and his papers are very fundamental, very important. This is one of his important, all of his papers are important, but this is a variant of score matching that he named slice score matching in 2019. Score matching is a popular method for estimating unnormalized statistical models. However, it has been so far limited to simple shallow models or low-dimensional data due to difficulty of computing the Hessian of log density functions. We show this difficulty can be mitigated by projecting the scores onto random vectors before comparing them. This objective, called slice score matching, because you project it, only involves Hessian vector products, which can be easily implemented using reverse mode automatic differentiation. And of course, it's computationally expensive. Therefore, the slice score matching is amenable to more complex models and higher dimensional data compared to score matching. Theoretically, we prove the consistency and the symptotic normality of slice score matching estimators. Moreover, we demonstrate that slice score matching can be used to learn deep score estimators for implicit distributions. So we show slice score matching can help deep energy-based models effectively. We can produce accurate score estimate for applications such as variational inference with implicit distributions and training Wasserstein autoencoders. So for the background, you need this paper in 2005. It minimizes the Fisher divergence between probability of the data distribution and your prediction, probability M, because you have theta parameter to learn it. So we are learning the score. But by applying the integration by parts, because we don't know this S sub D, as it says, do not have access to the score function of the data. So by applying integration by parts, again in 2005, Hiverinen, this Finnish guy, showed that L of theta can be written like this. So now in this formulation, there is no theta D. There is no data distribution, and everything is just a score, so we can train it very easily. C is a constant, J of theta plus C, but C is a constant and does not depend on theta. Trace here, this trace denotes the trace of a matrix. And gradient of a score function is the Hessian of the probability. So it's the Hessian of the log density. The constant can be ignored and the following unbiased estimator can be, because, we can always replace expectation with empirical summation. But, this is a difficulty that they noticed, computational difficulty. While the score matching objective avoids the computation of z theta, it introduces a new computational difficulty. Computing the trace of Hessian is, a naive approach of computing the trace of Hessian requires d times more backward passes than computing the gradient. Then here they talk about score estimation for implicit distributions. Score matching can also be used to estimate score of implicit distributions, which are distributions that have a tractable sampling process but without a tractable density. So we write the gradient, for example, suppose our learning problem involves optimizing the entropy of an implicit distribution. We can write the gradient of this entropy. So this gradient of G appears, it's easy to compute. The score is intractable, but can be approximate by score estimation. But what is the slice score matching, which is the idea of this paper? What is that? These vectors, projection vectors, V transpose, you project it. So V transpose, then V, so it becomes a scalar. Again, this becomes a scalar. So you project it and then you do the score matching. So we consider the following objective as a replacement of the Fisher divergence. So this was the idea that slice score matching. And of course, this idea is related to denoising score matching, which is still very popular, very important. By the way, score matching is very much related to, you don't believe if I say it's related to flow matching, because in flow matching, you want to learn this velocity field, because you don't know the true velocity. You want to learn it. And what do we do in score matching? Gradient of P of X minus gradient of P of data, for example. Your data you don't know. And of course, if you write the continuity equation, I think it's better to write like this. The probability, the derivative with respect to t is equivalent to minus divergence of p, the same probability here, times this u velocity that I'm talking about here, this u here. So you can see how your density evolves through time from the source to the target, from 0 to 1. Because we always scale in diffusion or score matching or anything, we scale the time so that it is between 0 and 1. And at each time, the vector fields go which direction you move in order to reach the target, starting from your initial prior distribution, which is simple known. And so you see this gradient, you can see how it is related to velocity. And that's, for me, it's very interesting that you can relate score matching to flow matching very well. And of course, this flow matching idea is just a continuous version of normalizing flows that you don't need to do push forward in discrete times, at particular time, and then doing several times. It's a continuous time. And so it's also related to normalizing flow. So everything is related to each other. Then they talk about kernel score estimators. Two prior methods for score estimation are based on generalization of this important Stein's identity. And here we have measure FID, Frege inception distance. It's just the distance between the mean and covariances, trace of the, because it compares the mean and covariance of feature representation. Of course, still even today, we don't have good measures, especially for graphs. That's why Yoshio Bengio recently worked on a new approach, new measure to compare different sets of graphs, the generated one with the true one, to see if the generative model working well.